In this series of videos, I'm attempting to repair what I believe is a TS800A. It's a combination of a dumb terminal and computer system. The dumb terminal side uses a 6502 processor and the computer side uses a Z80. You can see I've got this hooked up to the logic analyzer now. I've got the analyzer hooked up to the Z80. The status LEDs that we were looking at in the previous video are driven from the self-test by the Z80. So the Z80 goes through a self-test procedure when it starts up or when it's reset, and the status of that self-test is shown on the LEDs. Before I start looking at the analyzer and start trying to figure out what's going on with this, I thought I'd just clarify how this is organized, otherwise it might be a bit confusing. And the important thing to understand here is that the Z80 computer is completely separate from the terminal. So on the left here we have the terminal, the 950 terminal, and then we can effectively divide it down the center, and on the right we have the Z80. But I just need to clarify this a bit further, otherwise I'm sure I'll get a lot of comments saying, well, maybe there's interaction between the two. Because if you just look at these schematics, it can be a bit misleading. So I'll just move the camera a bit and we'll have a quick look through the schematics, and I'll explain how this is in sort of general terms laid out. So looking at these schematics for this machine, it's really divided into two completely separate parts. We've got pages 1 through 7 are for the 6502. The remaining pages are for the Z80 side of the board, but they are completely separate, even though if you just look at these schematics straight out of the technical manual for this machine, there appears to be a lot of crossover between the two sides. So for example, if we take the data naught line shown here, and it's shown as going to sheets 2, 3, 5 and 7. This is kind of important that we need to know where this connection goes to, and each connection or group of connections has an associated sheet number, and that's important. You need to look at not just the name of the signal but also the sheet number it goes to, because what they seem to have done here is taken the schematic for the 950, a schematic for the Z80 computer, and they've combined them into one set of schematics in the technical manual for this machine. But they haven't concerned themselves with duplications of signal names. And really there's only a couple of areas that we have crossover on these. They don't really share resources, they don't share RAM, anything like that. They don't share address bus, they don't share data bus. However, if we look at data naught, for example, it says sheet 2, 3, 5 and 7. But if we look on, for example, sheet 8, we have a duplication of those names. But if you won't be able to see this, but the sheet numbers are completely different. Remember I said that sheets 1 through 7 are for the 6502. So because these connections only go to sheets 2, 3, 5 and 7, it means these don't go anywhere near the Z80. And the same is true with a lot of the signals. For example, the reset signal for the Z80 is controlled from the 6502. So the 6502 can reset the Z80 computer. However, the reset signal throughout is identified as reset. So if you can see this, it's reset with a bar across the top, and that's consistent throughout apart from in two places. But that's included in here. So if we look on the Z80, it's also identified as reset, but that's not the same connection. If you try and buzz it out, you'll think the board's faulty. It's got exactly the same name, but it's not the same line. In fact, if we follow it through, so on here it says reset sheet 12, but if we go through to page 3 on this sheet, we'll see that we have this arrangement here, which is kind of the decoding for the 6502 to control the Z80. And if we come across here, you won't be able to read it, but it says Z80 reset, and it goes to sheet 12. So if we find sheet 12, Okay, and then what we have here is it says Z80 resets. That's where it goes to. But if you look across here, it's exactly the same connection, but it's just called reset. So in other words, that Z80 reset morphs into just plain old reset. So it can be very confusing, but don't confuse it with the reset that goes to the 6502. It's a completely different line. And like I said, the same thing is true of the address buses, the data buses, everything else. They're completely separate. The only other place they cross over is, and if you think about this, it makes a lot of sense. So what we have is the 950 terminal, the Z80 computer. They would normally be in separate machines. You'd normally have a dumb terminal, you'd have a Z80 computer, and a bit like connecting a dumb terminal to something like an Altair, you join the two together with a serial cable. And that's really how these two are connected together. If we look at the serial ports for the Z80, let's try and find the correct page. The serial ports are provided by two SIO devices. So this is one of the large-scale support devices for the Z80. And each one of these provides two serial ports. We've got A and a B for the first one, A and a B for the second one. One's for the RS-232 going out of the board to the outside world. That's referred to as the modem RS-232 in the technical document. We've got the RS-422, which is another one of these ports. And we also have this one, which is the internal RS-232 port. And this is equivalent to connecting the dumb terminal to a remote computer. In this case, our Z80 computer. And if we look at the sheet number on here, it says sheet 5. And if we find sheet 5, we have those same lines coming in here, and this says sheet 13, which is the sheet number for these connections. So these connections go to here, and it's really just a serial connection going between the Z80 and the 6502 dumb terminal. And this is the only real connection between the two. It doesn't share data buses, doesn't share address buses. It just communicates through this serial link in the same way a dumb terminal would normally talk to a remote computer. So just bear that in mind as we go through this video, because otherwise you might be thinking there's maybe odd interactions between the data buses on the 6502 and the data bus on the Z80 and that sort of thing. The only connection between the two is the serial port. So we'll go back to the PC and I'll explain how I've tried to minimize the possible interactions. So what I've done to try and get the Z80 to go into its self-test is I've removed the 6502. That allows the reset to be released for the Z80, so it comes out of reset, should start to run. And I've also unplugged the two SIOs, so there's no chance of the 6502 system doing anything. It probably wouldn't anyway, because with the 6502 removed, there's no way to generate serial data. I didn't want just noise and possible rogue data finding its way into the Z80 system. So I've got the logic analyzer connected to the Z80. All the lines are connected. This is the usual way. I've shown this before. And I've also extracted the code from the ROM. So this is, you can probably tell by its location on the board, it's on the Z80 side. I've extracted the code from that and I've disassembled it. I've tidied it up a bit, and we're going to try and trace that through with the logic analyzer. So I've printed off the bit of the code I think is relevant to us at the moment. And what I've done here is I've disassembled the code, and the next thing I do in general when I start a process like this is there's about 60 pages of code. It's a relatively small ROM, it's only a 4K ROM. So about 60 pages or something. And what I do is I go through that and I find all the return instructions. And as long as it's not a return with a jump before it, in other words, if it's a jump if something, and then if the follow instruction is a return, I ignore it. But if it appears to be the end of a function, then what I do is I put spaces between that return and the next instruction. And in theory, what it will do is it will subdivide the code into logical blocks, usually small subfunctions. And what I did then is went through and searched for all the in and out instructions. And in the technical document, there is a useful couple of pages that list what all the ports are for. In fact, it doesn't list all the ports. There are some in and out instructions that aren't listed here. I need to figure out what they are. So, for example, port 0, these are port addresses. Port 0 is the dip switch. That's our switches that are for configuration. And then the memory latch, for example, CTC channels, the serial in-out channels, that's the ports that are used to access those, floppy drive controller channels, and the LED status channels. So knowing this, what I can do is go through the code and start to comment it before we even run it. So for example, our port 0 is the dip switch, so I know that an in instruction of that port is reading the dip switch. So I did the same thing and I figured out that this bit of code is probably the start of the RAM test, which is the first test it runs and the one that appears to be failing because the first LED is flashing. So what we'll do now is fire up the logic analyzer, try and find this bit of code and try and figure out what's going on. So this is just the general setup I have, the generic setup for a Z80. All the lines are connected, it's set to state mode, and I'm using the Z80 clock as the state machine clock. So looking at the code, what we'll do is see if we are actually getting to this part of the test. And the reason I believe this is part of the RAM test is it's got a 4K ROM. This is loading an address of 1000 hex, which is the first byte above the top of that ROM, so it's in other words the start of RAM in this bank, and then it appears to be trying to write 100 bytes of it's a value that starts off with the number, it's a number of bytes it's writing, but it decrements the value, so it's a different value to each RAM address, and then it compares the value in A to see if it's written all 100 bytes, and if it hasn't, it loops and carries on till it has written 100 bytes, and the next bit of code it's doing the reverse, it's counting back up and checking if it has successfully written those bytes and if they match what it is expecting. So if we come to this point, see if we get there at all, and see what we get. The other thing I don't know is what this arrangement here is. The port 18, I need to try and figure out what that is, but certainly it might be important. If this is failing, it could be whatever this is supposed to be doing isn't working. We'll see if we get here first. I'm going to set the address of 33A. It's going to dim the lights a bit in here. Okay, so we've got that set. The machine is currently turned off, so we'll arm the analyzer, switch it on and see if we get to this address. And we are doing, so that's a good first step. And the next thing we're looking at is the value that's there, which is the disable interrupt. And that, if I have to turn the light back on, it's not really showing up very well. Hopefully you can still see the analyzer screen. So the value we should have at 33A should be F3, and as you can see, that's exactly what we're getting. And the one at 33B should be 3E, which again is correct. So we can now go through and see if it's actually going through this bit of code. We can just scroll through this and see how far we get. And if this is working, we should come down to this point and then keep looping round to an address of 344. So we've got 344 here, and the instruction there should be 77, and this is where it's loading the value that's in A into RAM. So we'll see if we keep going round. So we are indeed getting to 344 repeatedly, and not only that, but you can see that the address value, which started off at 1000, is incrementing, and the value in A, which started off at 64, is going down. So if we go to the next one, we should see that address has gone up and A has gone down again. So we've got address 1002 and a value in A that we're trying to write of 62. So that loop seems to be doing what it's supposed to. More importantly, we definitely seem to have got the right ROM, and the code does seem to be being read by the Z80 because it's the right values that we're seeing. In other words, the data bus and address buses seem to be doing what they're supposed to. The next bit we're interested in is when it starts to try to check this. So if we go to the line where it's starting to do the checks, so that would be down here. This is where it's comparing the value it's written. We need to go to address 34C, and rather than scrolling through this because it'll take quite a long time, I'm going to just rerun it, but with address 34C as our trigger target address. Incidentally, the LED on the board is flashing as it was before, so we are just looping around somewhere. So I'm going to reboot the machine, turned it off on the analyzer, turn the machine back on, and we have indeed got to the correct piece of code. So we're now at this point where it's trying to read the value back from RAM. The value we should see for the instruction is 04, and that is indeed what we're seeing. That's here. Remember that the refresh cycles are also running here, so it's dynamic RAM, of course, so you need to bear in mind that the intermediate values we're seeing that are counting up are doing that because they are the refresh cycle values. So here it's saying 3C, 3D. These are two refresh cycles, so don't be misled by those. Just ignore those for now. Okay, so 3.4. Okay, so what we're looking at here is A, which got down to 0, was loaded into register B. That was incremented, so that is now a value of 1. And the HL value, that's been decremented, so that will now be pointing in theory to 1063, and we then load the value of that address into A and see what we get. So if we scroll across, okay, so address 1063, okay, we're getting a value of 0. That's not right, we should be getting a value of 1. So it's going to compare the value in B, which is loaded with 0, incremented, so it's looking for a 1. If it doesn't get that, it's going to branch to an error. If it does get that, it will check the next byte, checks if it's got to the 64 hex starting point, loops around checking each byte. I suspect it's going to branch because that's the wrong value we're seeing, so chances are we're going to end up at address 35A. So let's keep scrolling across, and we have jumped to 35A. So that test, not surprisingly, has failed. It's read the wrong value from RAM, and it's read a value of 0, which is interesting. So it's not just random garbage that I was kind of expecting it to do. And let's just try and see where it jumps to next. So it's going to jump back to just trying to find out where it's going. I'm kind of ignoring the instructions file. I'm just trying to look at the address to see where we're going to end up. So looking at the code, this should return to the calling function, and what's odd here is one thing I didn't mention is when the processor starts up, it loads a value into the Z80 stack pointer of EE20, and it's performing calls here and returns, but we're never seeing anything like that address appearing on the address bus. So as I said, so what it's done here, it's actually jumped back to address 0, so it's effectively reset itself. The first 30 or 40 bytes for some reason in this are zeros, so there's knobs, probably just to allow a bit of time for things to settle down before the code starts. So it will then obviously loop round and do the same thing again, and these addresses here, 000A, B, C, are the first few addresses in the ROM. So when it returned from the function that it had jumped to do the RAM test, it returned to 000 instead of the return address. So that's not surprising. The value we got from the DRAM when we were trying to do the memory check was 0000 as well. So it looks like that value is always returned from RAM, and that includes when the processor is trying to pop the return address off the stack, and in this case that's obviously going to cause it to reset. So it looks like the issue at the moment is that the value being returned by the RAM is always 0, irrespective of what's been written there, and then obviously is going to cause a few issues. So I'll just move the camera back down to look at the board. So what I can do now is start hunting through it and trying to figure out why the RAM is not returning a sensible value, and if we can figure out why that's happening, it could just be there's a fault in one of the glue logic chips. They are brand new DRAMs, so I know they all work, so it's not that. Did have a stuck bit when I first started trying this, and hopefully we can figure out fairly quickly why this self-test is failing, and then probably move on to the next. The 6502 doesn't run either, so we'll need to treat that as a separate repair almost, but the first thing I want to do is get the Z80 at least running to a certain extent, so that it's not going to hamper the 6502 repair when the 6502 is interrogating the Z80 for information. As you can see, I've unplugged the clip from the logic analyzer, and that's we don't need it just now. We might have to put that back on if we can figure out what the memory issue is, but we know what the system's currently doing, at least the Z80 side, and we need to try and figure out why the value coming back from the DRAM is always 0. I did try it a few more times off camera, and it does return 0 every time, so every time it goes through the self-test, the value it's returning for the first byte that it's tried to write is 0, so that's obviously wrong. So getting the correct section from the schematic, find the RAM, and there's a bit of a clue we've got already that it's always a 0 value that's returned. So these are our DRAMs. Quite a simple arrangement. Now of course we do have to deal with the strobing of the DRAMs and the two-step addressing. If you're not familiar with that, then if you watch my series on the Z80 computer design, I do go into driving DRAMs in quite a lot of detail. But here the clue is that we're always getting a 0 back. It's not a kind of random value or a stuck bit or something like that. It's always 0. And normally that means that the DRAMs are not being put into the mode where they're outputting data. So in brief, to get a DRAM like this to output data, you need to set up the first part of the address. We supply the address in two 8-bit chunks. You set up the first 8 bits, latch that into the DRAM with a strobe, that's the row address strobe, and then you change the address for the second half of the address, latch that in with the column address strobe. So I suspect that one of those two is missing, so we'll check those out, and the easiest place to do that is on the DRAMs themselves. So the row address, which is the RAS, is pin 4, and the column address, which is CAS, is pin 15. So we'll look at those two pins and try and figure out what's going on. So we'll start with the RAS signal. So I'll power the computer up and we'll look at pin 4, which is our RAS signal. The LED is flashing again, hopefully you can see that. Let's move the board back a bit. And you can see we are indeed getting the RAS signal, so that's looking fine. The reason for the variations in pulse width we are of course also getting the refresh updates. It's RAS only refresh on this board, so we'll try seeing if it's any different when we first boot up. It looks fine, and now we'll look for the CAS signal, which should be on this pin. Nothing there at the moment. Okay, well clearly something is not right there. We should be getting a strobe on that pin. Let's try one of the other ones, make sure it's not a board error. I'm resetting the board because, as we saw, it's only reading 100 bytes, or writing 100 bytes and then trying to read it back. So we're only going to get a quick burst of CAS signals. The RAS will be there all the time because that's part of the refresh cycle, but clearly there's nothing coming through to the DRAM in terms of the column address strobes. If we grab the schematic, so that should be coming in here, and it's originating on sheet 10, which is the sheet prior to this one. So we've got the CAS coming out here. So what I'm going to do now is just work my way back through here. This part of the circuit will just be deciding what decoding to use and the sequencing for the RAS and the CAS, and the select is going to be the strobe select, the multiplex select. So we go back to this page. Yeah, it's connected to here. These two multiplexers are used to switch between the two halves of the address that are being supplied to the DRAM chips. Just out of interest, we'll just see if we're getting anything on that line to see if there's any strobe and selection going on there at all. So I'll try and do this without blocking your view. Okay, so I'll reset the machine. Okay, so there's nothing there either, which is not a surprise. It's driven from the same part of the circuit. So clearly we have an issue here somewhere that we're not getting the signals coming through that we should. So either there's an issue with the decoding to select the DRAM, so we've got the decoding here to select the EEPROM, we know that's working, but there's something amiss here, or the signal further back is not being driven as it should be. I suspect the problem's in here somewhere, so I'll start working my way through this. All I'm going to do is check each of the relevant devices that are in this particular signal path and see where the signal is getting lost. Okay, well, it didn't take long to locate the fault. One of these 7474s was not doing its thing, and that was pretty much in the path that we expected. So we've got the CAS signal coming out here, and despite getting the proper clock and also getting the proper request for DRAM, this flip-flop was not doing anything. There was no output. It was always staying low, which meant that this was never being enabled, and so the CAS signal wasn't getting to where it should do. We were getting the proper strobe signal coming through, so the timing was correct. It's just the gating for the CAS wasn't working. So I took that IC out, put a new one in. This is the one I've taken out. If we do a test, it does indeed test as faulty. Another reason I try and get them out intact. So what we'll do now is we'll power the board up. It's not going to get all the way through the self-test, even if it gets any further, because I have certain ICs removed. But we'll see if it gets any further. If you recall, when we turned it on before, the first test LED was coming on for half a second, and then it started flashing to indicate a fault. So we'll turn the board on, keep an eye on the LEDs. Looking more promising already. The test is still running, and it's moved on to the second test, and that is now failing. Now, The second test is the DMA test. Now I knew that was faulty already, I think I mentioned that in the previous video. So the next thing I'm going to do is swap out the DMA, and we'll see if that allows us to get any further through the self-test. The RAM test was passing every time. I did try it a number of times, and what I've done now is fitted a replacement DMA controller. That's the test that was failing last time, and this is the second LED, the bottom right LED as you look at it. So we'll see if fitting a new controller has cured that particular problem. If it has, then that LED should go out and it will move on to the next test. So let's give that a go. So the RAM test is underway, and the DMA test passed, LED went out, and it's now failing the next test. That test is for the SIO devices. Not surprising, that's failing, they're not plugged in. I don't know if they work, I haven't actually tested them, but we'll test these now by plugging them into the board. Okay, we'll try and power this back up. Like I said, I don't know if these actually work, so this might still fail. So RAM test. So that test seems to have stalled. It's getting further than it was. It still may be because the SIOs are faulty, or it may be because it's waiting for a response from the 6502 to one of the test steps. So in the next video what we'll do is we'll hook the logic analyzer back up and see what the test is actually trying to achieve. But we're certainly getting a lot further now.